The next slide, we'll take a look at defect classification and really 5 types of disorders in stoichiometric crystal MX are identifiable. Frankel disorder, and Frankel disorder on M sublattice with equal number of vacancies on the M sublattice and the M interstitials. Frankel disorder on the X sublattice with equal number of vacancy on the M sublattice and X sublattice, and equal concentrations in M on X interstitials, and anti-structure disorder on M ions occupying X sites and X ions occupying M sites. So these manifest themselves in terms of atomic defects such as Frankel disorder, Schottky disorder, and so we'll take a look at anti-structure disorder, electronic defects, which include excess electrons in the conduction band, electron holes in the valence band. Uh, Secondary defects includes impurity vacancy pairs, M vacancy, X vacancy pairs, trapped electrons at defect contribution holes to valence band. Defect act as donor and contributes electrons to the conduction band. So with regards to preference of a crystal for Schottky or Frankel defects, it is more difficult to make quantitative calculations. Generally speaking, more closely packed structures, Schottky defects are preferred since the energy to move the M plus ion into the interstitial would be larger than the formation of an ion vacancy. So for more open structures and for compounds where the cation is much less, the anion radius R, the energy of formation of the interstitial M ions become less than the anion vacancy. So the Frankel defects on the cation sublattice will be the primary form of disorder. In general, substitutional disorder is not important for crystals with predominantly ionic bonding because of the mismatch in atomic size and charge. But as the bonding become less ionic, the atomic sizes become more similar. Substitutional disorder becomes important. Substitutional disorder are less important are selected thin film optical materials, silicon dioxide, zirconium dioxide, tantalum peroxide, aluminum dioxide, and titanium dioxide, where electronegativity difference between components M and X are large, and hence the size and valence differences will be large. So for cation energy of vacancy formation, as we see in the next slide, is given by equation 17.1, and for the ion vacancy formation given by equation 17.2. For the energy of formation for Schottky defect, 17.3. In these cases, A is the Madelung constant, E is the electronic charge, R plus is the, and R minus is the cation and anion radius respectively, N is the Born exponent, and K the material dielectric constant. In the next slide, we show the calculations of defect formation energies for selected thin film resulting from these equations. And we're looking at, in terms of structure, silicon dioxide has a hexagonal structure. Um, its Madelung constant is around 2.2. Electron charge 1.6 times 10 to the minus 19. The cation radius is 4.1 e to the minus 11, and the anion radius is 1.4 e to the minus 10. The Born exponent 7, material dielectrons constant 3.9. So we end up with a net energy or Schottky energy of 6.68 times 10 to the minus 29 joules. And so zirconium dioxide is monoclinic in terms of structure, titanium dioxide tetragonal, tantalum dioxide orthorhombic and aluminum oxide rhombohedral. However, we performed the same calculations, and it turns out that the tantalum so from this data, one can see that the highest defect formation energy is for the monoclinic zirconium dioxide, and this was followed by tantalum pentoxide, and then by titanium dioxide.